Okay, so let's continue with our review. Um, we will now continue on discussing formal charges. So with formal charges, basically, the bottom line, the reason we have formal charges is just to see it, where the charge resides. Now, when we have something that's neutral, we might not have an overall charge like an ion. The formal charges lets us see what's happening. So let's, for instance, let's give you nitrate. So when we draw our Lewis dot structure, we find that it's trigonal planar. And what do we have in drawing structure? Something like this. And when we do this, what are the formal charges? Well, it turns out each atom isn't really quite as neutral. So a formal charge per atom, how we calculate it is going to be the number of valence electrons minus 1/2 the number of bonding electrons minus my lone pair electrons. Okay. Sometimes you'll see me talk about it where once you draw, now you can't do this until you draw your Lewis dot, but once you draw your Lewis dot structure, sometimes I'll say a formal charge is basically equal to your group number, since we were saying that our group number for our main group nonmetals in particular, but our main group elements is the group number equal to their valence electrons minus the lines minus the dots. So always make sure you draw all of your lone pair electrons. So if we do this, then what we find is that the top oxygen right here is going to be 6 minus 1, 2, 3, 4, 5, 6 minus 1. That has a formal charge of a -1. This one, this oxygen has a formal charge of a -1. If you look at this oxygen here, then it has 6 valence electrons minus 1/2 my bonding electrons, that's 4. Okay, so 1/2 of 4 is 2, so it's like 2 lines minus 4 dots. So this is 0. So we don't write a value if it's not positive or negative. If it's 0, we leave it alone. What about the nitrogen? Well, it's 5 minus 4, so this is a positive. So it turns out nitrate, the sum of my formal charges is equal to the charge of the ion or molecule, or it's 0 for the molecule. In this case, the sum is -2 plus 1, so this is, the sum is -1, which is what we see here. So that's how we calculate formal charges, okay? And it's useful when we get to resonance. So let's talk about resonance next. So resonance, remember, what we're looking at is we're looking at different electron positions or orientations, okay? So in other words, let's take our nitrate, for example. We're now going to use different colors for each oxygen. So I had oxygen up here. I had oxygen down here. And I had an oxygen here. So what we're interested in is in the different ways we can orient our electrons. That means the bonding patterns, right? The bonds. What we're not going to do is move our atoms at all. So how do we do that? So basically, we typically use, when we're trying to show you we're moving our electrons, we use curved arrow notation. Curved arrow notation looks like that. This is where you start. This is where you're moving your electrons to. So that'll be the final position. A full-headed arrow here means 2 electrons. If I have a half-headed arrow, this is moving 2 electrons here. This one, you move 1 electron. Okay, so let me go ahead and show you what we can do. If I take 2 of these purple electrons and I move it to form a bond between the oxygen and the nitrogen. Remember, the nitrogen can only do an octet, so I have to move these 2 electrons onto that oxygen. To show that what we're drawing is going to be a resonance structure or a resonance form, use a double-headed arrow. So we know that we're looking at a resonance form. And when I redraw this, so I'm just going to use the same colors, just so you can see I did not move my atoms. I only moved my electrons. So I have 2 that I didn't touch here. And then I moved 2 to be between the nitrogen and the oxygen. Here, I move 1 of the red bonds. Remember, a red bond consists of 2 electrons. So 2 of those electrons goes here. These other lone pairs stay here because I didn't touch them. So for my oxygen that's green, I didn't touch anything, so I just redraw this. And now we calculate our formal charges again. Why do I have a mark here? Sorry, there's no formal charge on this oxygen. Let me get my color back. There it is. Okay. So what happens now is you draw the arrows to indicate where you want to move your electrons, and then you move your electrons. Okay. All right. So what about another resonance form? So let's go ahead and take these green electrons and I'll move them down. I'm moving 2. So then I have to move these 2 back up here. So if I do that, double-headed arrow to show what I'm doing. This is where I want to move everything. So again, let me go ahead and draw my structure again. And I haven't drawn my electrons yet. So I have 2 lone pairs here and here. And I took this lone pair right here and I moved it to be the bond between the oxygen and the nitrogen. On this oxygen, I took this lone pair and moved it back up. So these lone pairs I didn't touch, but I have a lone pair that came from this bond. And my red oxygen, I just copied in place because I didn't do anything with it this time. So now if we calculate our formal charges, that's a minus. Plus here, we're not doing. I'm so sorry. And I have a minus here. Okay. So that's how we do resonance forms. Now a resonance hybrid, Because resonance forms is not an equilibrium. You're not going from one form to another. It's just showing that we are limited in our ability to draw a resonance form. So you might see us talk about a resonance hybrid. And a resonance hybrid is kind of like the summation of what we're trying to indicate with our resonance form. So my resonance hybrid, these bonds between the oxygen and the nitrogen are not single bonds and they're not double bonds. They're basically 1 1/3 bonds. Okay. The formal charge on the nitrogen is still positive, but each oxygen has a partial charge of -2/3. So that's my resonance hybrid. And this is only to indicate that my bonds are not single bonds, they're not double bonds, but in this case, they're basically 1 1/3 bonds. All right. The more useful ones is actually the resonance forms. So typically when we talk about resonance, you'll see us talk about and draw resonance forms more frequently than just basically the resonance hybrid. So let's go back. Okay, so we talked about our formal charges. We talked about resonance. So let's talk about structural formulas. So when we talk about structural formulas, what does that mean? So let me just give you a Lewis dot structure. Okay. And this has a molecular formula of C5H12. Okay. So drawing a Lewis dot structure where all of my bonds are explicit can be tedious at best. So what are ways that we can actually draw this in a more condensed form? So when we talk about condensed structural formulas, what we basically do is exactly what the name says. We try to condense them into groups. Okay. Now, when we write this, that's a CH. Oh, excuse me. A CH3 group, followed by a CH2, 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 CH3. Now, when we draw it this way, we basically assume that the carbons will be my central atom. So to reverse it, we say I have a carbon and it's bound to 3 hydrogens. But as you know, carbon, to make sure it has an octet, needs 4 bonds. So it must mean that the next thing it's bound to is a carbon. Well, the second carbon has 2 hydrogens to it, but in order to get its octet, I need to have another bond that's bound to this CH2. Okay, so going in reverse, you can see that to make sure all of my atoms have their octet, we find that in this condensed structural formula, they're all bound to each other. The carbons are bound to each other. Suppose I gave you a structural formula that looks like this. Okay, if I say, give me the Lewis dot structure, then you'd say, well, this is my first group, CH3. In order to satisfy my octet rule, this must be bound to a CH2 group. get my octet, I must be bound to another CH2 group. And then what must this carbon bind to? It must have a bond to the oxygen in order to satisfy the octet. The oxygen, because I have a valence of 6 valence electrons, so I have 2 bonds that I can do to achieve an octet. I have a hydrogen here and I'm bound to the carbon there. So this is my Lewis dot structure. And then this is my condensed structural formula. So what about line angle or skeletal? Screen, so I apologize about that. So line angle or skeletal drawings. So the way this works is that we assume the hydrogens when bound to carbons. The carbons are at the ends of lines or the intersection of lines. Okay, so I'll show you how those look. And then also heteroatoms, so non-carbon hydrogen, are drawn explicitly. And the hydrogens on the heteroatoms tend to be drawn. Lone pair electrons may or may not be drawn. Okay, my preference is to have them drawn. Okay, so what does this mean? So if I draw something like this, then when we talk about at the ends of the lines, I have one, one, two, and sorry for the wiggle there, 3. So this has 3 carbons. The end of the line or the intersection. Okay, so how many hydrogens do I have? So for the hydrogens, if this is my carbon, carbon can have up to 4 bonds, right? If it has less than 4 bonds, it's going to have a formal charge. I don't have any formal charges yet. So I have 1 bond. That means I have 3 more bonds. It must mean I have 3 hydrogens here. In this carbon, right here, I have 2 bonds. So carbon should have 4. Therefore, on this carbon here, I have 2 hydrogens. And then on this end carbon, I only have 1 bond, which means I have to have 3 hydrogens. None of the hydrogens are shown, okay? So we are assuming hydrogens. We're not showing them explicitly. Therefore, this now has 3 carbons, 8 hydrogens. Let's draw you something that has a heteroatom in it. Okay, I'll draw my lone pairs because that's my preference. Okay, but you'll sometimes just see it without the lone pairs. There are no hydrogens on this heteroatom. I have one carbon here. I have one carbon here. Since I only have one bond, I have 3 hydrogens and 3 hydrogens. So if I drew out my condensed structural formula, this would be CH3, O, CH3. Okay. So that's how we do line angle. What's the advantage of line angle? So let's go through the advantages of each. The advantage of condensed structural you can see each group explicitly, so we're not assuming anything. Okay, and it can be typed, your formula can be typed in a single line. Okay, so it can be good for a lot of linear type compounds. And they tend to be, they're good for linear compounds, and they're also good for smaller compounds. Okay, and you don't have to draw as many explicit lines as you would with your Lewis dot structures. The hard part is when you do cyclic compounds are still difficult. Okay, they can be drawn with a condensed structural formula, but the cyclic compounds can be bulky to draw using condensed structural formulas. What about line angle or skeletal? The advantage of line angle drawings, it really shines when we have cyclic compounds and we have larger compounds. So larger compounds, branched. Okay. So these are very common. You'll see us use line angle quite a bit. Okay. So those are some of the advantages behind why are we moving away just from Lewis dot and being able to describe our structures using condensed structural formulas or line angle formulas. So now that we've done this, let's go to acid-base definitions. And I will do that in the next video.